Okay, everybody, welcome to our 13th lecture in ECE 576 for this semester, and this is our last lecture. This is a little different in terms of the topic that we are going to cover today. It's now at the other end of information engineering where we do learning. So what we have seen now, up till now, is how do we represent information, how do we compress it, how do we store it, and all those theoretical ideas. And then at some point we went into inferring information. So we said, okay, if we represent information as probabilities and represent them as graphs, can we do inference over them? And after the inference topics, we did something about estimation. So let's say you had data, like you had samples of or observations of the quantities. How can you actually go and estimate probability densities or distributions from them? So it kind of, it's a natural flow, top to bottom, where you first see the top level ideas, and then you can actually go down and towards the data level and start to estimate things. Now, the next frontier in estimation or kind of working with the data is called learning, right? So that's what we're going to study in our last lecture here. I know this course has a wide variety of topics, and that's the whole idea, to give you a overview of the many different areas that are related to information engineering. And hopefully when you encounter these next time, you will have a better idea of what you are looking at. So this lecture is really a brief overview of machine learning. And artificial neural networks. The details you can learn when you have a specialized course on any of these topics. So it's artificial neural networks. I mean, I'm sure some people would already have some idea of what the whole machine learning idea is, but from from a very theoretical perspective, the idea is, can you find a mapping from the input to the output? So I mean, in general, we have mathematical functions that you represent by the symbol f, right? So that's a function that operates on the input. So if we had input xi, right, you have an output which is yi. And the goal of machine learning is really to find out what the f is if you have the input and output pairs. Right, so this is really the crux. So when you're in calculus, you're already given functions. This is a mapping. You provide some inputs, you will get some outputs, and those are generally smooth functions, which are pretty straightforward. So you just plug in the input, you get the output. But let's say when you have when you don't know the mapping, but you just know what the inputs were, what the outputs were, then how do you learn a mapping? That's the idea behind machine learning. And then there's many ways to do it. Depends on what the problem is and what you are trying to achieve. So it's to find the best function that maps inputs to outputs. Okay, so if you look at machine learning as a field, there are several different types of them, several branches, and the classical ones are, it's obviously evolving, so you'll have new forms of them, but the most well understood are supervised learning, and then you have the unsupervised learning. Right, so these are kind of the very broad categories when we talk about machine learning in general. Nowadays, people have started to kind of mix them up and say, okay, well, why can't you have something in between, which is called semi-supervised. Okay, and another broad category, I think, which is recently gaining a lot of attention again, is something called reinforcement learning. Again, this is a separate topic in itself, so we are not going to talk much about it. It's a slightly different way of learning things in which you don't have the classical input-output stuff, but it's like going out and experimenting. So you try something and you observe something. So it's kind of collecting that data on the fly. So you don't have already the input-output pairs, and that's why we are kind of classifying it differently. So supervised learning and unsupervised learning further have many different categories, and we will briefly talk about them before we kind of focus really on the artificial neural network part. So the supervised learning category can further be split up into two classes. One is the regression, okay, and the other is the classification. Now, in one way or the other, I know you would have encountered these things in many different courses, and even high school, they teach you regression or data fitting, as people popularly call it. So regression is often called data fitting. Right, so you must have seen least squares fitting or something of that sort somewhere in your life. So that's really a supervised learning category. And the reason why we say it is supervised is because you already know the inputs and outputs, right? So you have labels to data. So it's, let's say, the reason I call it supervised is because the data is labeled. Meaning I know what is the output to a certain input. And when I say it is unsupervised, meaning that the data is unlabeled. Okay, and we'll see what this really means as we go on further in this lecture. So so basically, first thing was the regression, and regression is data fitting, and which essentially means you had a set of inputs and outputs. Let's say in a one dimension, it is just a set of points, right? And the problem really is, how can you find the best fit? So really you have to find the mapping from X to Y. That's your regression problem. So this type of technique or this type of learning strategy is often used in a lot of different things. One of them is called prediction, right? So if you want to predict what is going to happen in the future based on past data, you do a regression analysis. You try to fit the data with the best possible mapping and then use it to predict on the future. You can also do trend analysis, kind of knowing what trends are what trends are going on based on the data. Obviously, there are subtle details to this fitting and the way people fit it. You might have heard about things like overfitting, where you kind of end up in a very overfitting kind of situation. So that's something people have to take care of when they're trying to do regression based fitting. But that's a topic for another day, and it's really in the details that this comes up. So the general idea here is that if you have labeled data, you can either do regression on it, or you could do classification. Again, classification is kind of labeled problem. You have inputs and outputs, and you have labels, but it's slightly different in the way that you have data that has labels. So you can be in a two-dimensional space, and you could have a third dimension that represents labels. So for example, if you had points, two different type of points in your XY space, and you want to separate them, or you want to figure out what is the category of the next label that you have. Let's say you have another label here. Which one should it be? Then that's a classification problem, because you have to categorize it. So the essence of classification is, how do you draw the line that separates classes, right, or categories? So in general, classification would mean partitioning. So you want to partition your data into classes or categories, and that helps you to make some conclusions on new data or new samples. I mean, for example, if you it's just like let's say you have a scale for BMI, body mass index, and there are people who are overweight, and there are people who are marginally overweight, or there are people who are underweight. So these are kind of categories, and somebody has done the classification. So it's you've kind of partitioned the space, and when you put yourself on the map, you are somewhere, and there's a category associated to it. So how to draw the boundaries is a classification or a partitioning problem. Okay, and some popular applications to this are, one of them is the image classification. And another one is diagnostics, right? Could be medical diagnostics, could be engine diagnostics, right? Can be any kind of classification. Okay, so this is for the supervised learning part. Just a very brief overview. So if we look at unsupervised, which means you do not have labels on the data, which essentially means you just have data and you need to figure out what whether there are some categories, then sort supervised learning. So one of the most important category in this form is called clustering. Again, you might have heard about it somewhere, one way or the other, but more formally, it is part of the unsupervised learning techniques. And the other category is dimensionality reduction. Dimensionality reduction. Okay, so clustering really is kind of segmentation, where you partition in some way your data according to the structure it has. So for example, if you had data which is in some way clustered, right? So when I say clustered, meaning it has some kind of togetherness in it. So some data are similar to the others. I mean, let's say, for example, you had data points which are, in some clusters. So this is one type of data. Then you have data which is data points which are in another cluster, and then you also have another. But all of these are data points, so you don't really do not know what is going on. It's just their locations are in certain clusters. So visually you can see it, but how does the machine figure it out? That's really the question. And when the machine does it, it's really called clustering. So machine will figure out this is the first cluster, this is the second cluster, and this is the third cluster. And whenever you have a new point, let's say you have a new point here, then it has to be associated to some cluster. So, I mean, the goal of this technique is to figure out what the boundaries are. Where do you draw the lines, or the partitioning, for which if you had a new point, you could associate it with an existing cluster. Okay. So this type of technique is used in some applications as well, and one of them is called recommender systems, right? So when you make people recommendations, you have to be sure that they are in some way similar, and then you kind of give them similar adverts or recommendations, things like that. Okay, and the other one is the targeted marketing. Right, so essentially, to understand this, maybe you can think about recommendations being given to you on Facebook, on LinkedIn, about people you may know, people who could be your potential contacts. How do they figure that out? There are many techniques to do it, but the broader idea is they've kind of clustered you in some sense. Okay, and that comes with the different levels of similarities. So if you are similar to other people, then you may also be interested in things that they are interested in, and that's how the ecosystem works. So there's some learning going on, right? Everybody is a data point. Every user of Facebook or LinkedIn is a data point, and they have to do some unsupervised learning on you or on your activities to figure out something. So it's really not labeled. You don't know what the category people are in, but you could see their activities. You could see their characteristics, and using that, you have to kind of learn what category or cluster you're in. Now, the last one, or the most important last category, is dimensionality reduction, also called as compression. And it's also a very useful technique. I think a lot of people use it in image analysis, even in even in suggesting people their kind of recommendations. I think this techniques comes in handy. So what it tries to do is it extracts the most dominant components in the data. So instead of having so many data points or so many details, you try to represent it in a smaller dimension. So as an example, let's say you had a set of data points in the 2D space. This is a very simple example. So what people try to do is they find out what are the components here. So what are the so how can you represent these data points in a short dimension, right? So these are, like, let's say 100 points. So how do you represent them in a smaller dimension and kind of compress this, but still have some sense of the same information? So here, one way is to represent them as vectors. So with some direction. So this data here, you can represent them with the two vectors. One is E1, the other is E2 here. Okay, so it tells you that most of your data is aligned towards E1, and the length of E1 is telling you how far across this line the data can be, and E2 is a measure of the spread. So it tells you, your data is kind of spread around. I mean, this much along this line. Now, if you had another data set, you could again use these two vectors, and let's say that new data set has these vectors. Then comparing these vectors is easier than comparing all the data points one by one, right? So this is a very useful technique because you kind of summarized your data with the help of vectors, and that gives you important information about the structure of the data, what spread is there, instead of having to compare everything, you will just figure out if two data sets have similar vectors, or the vectors are very close. I mean, let's say you had two data, but their vectors are like this, then they are almost similar. So so that's how Facebook or LinkedIn can again figure out who your possible friends could be, because let's say this red one is one user, the green one is another user, and their activity trends are these black points. So if two users have a very close set of vectors, you could know that they are very similar. And if you want to compare vectors, there are measures like cosine similarity. So people can actually measure the angle here and take the cosine of the angle that gives them the dot product, and then they can figure out how close the vectors are. Okay, so if the angle is 0, that means they are the same, but if the angle is small, then you could tell that the vectors are close enough. So anyway, this again is a very useful technique, and two of the main kind of algorithms or strategies are principal component analysis, people also call it ECE, okay. There's also something called feature extraction. You can also call it structure discovery. Okay, so all these are a way to do dimensionality reduction of the data. So these are all very diverse topics, and again, they are domains or fields in themselves, and obviously we don't have time to cover all the details here. So we're going to focus on mainly the clustering, or sorry, the classification topic here, which is it's in some way it's used a lot, and the reason is you have labeled data, you have labeled examples. So I mean, it makes it may be more helpful to all of you. So and again, neural networks are also used in classification applications a lot. So so we can focus on this one for this topic. Okay, so let's see what the classification problem really is. When we say classification, we basically mean we kind of want to identify which class or category a certain input data belongs to. So we want to identify which class or category the input data belongs to. Okay, and popular examples of this, you know, if you study machine learning literature, the very classical examples would be, can you classify whether an email is a spam email or a ham email? Okay, and similarly, people use it in medical diagnostics. So if you had a tumor and you can see the size of the tumor, can you actually classify it into a benign tumor or a malignant tumor? Okay, and you know, there are data sets that you can try different algorithms on, and you can see how accurately you can classify the inputs into the correct classes that they actually belong to. So you have data which is labeled, meaning you already know there are emails that are actually spam, and the goal is to learn a classifier or a function which, if you give them a new email, it can tell you whether it is a spam or a ham. So that's a learning philosophy. I mean, there's a brain you're trying to train into having the ability to separate an input email into a spam or ham email. Now, how do we do this? We could use different techniques. The most simple ones are called the linear classifiers. So as you know, we love linear functions because they are linear, right? They are simple to deal with. So every time we are faced with a problem, we like to resort to some linear stuff. So linear classifiers, just like we showed you here in this example here, if you want to separate this data or classify it, we just use a linear classifier. Maybe linear is not the best, but at least it will give you some classification in an easy way. Okay, so they map inputs to outputs. Based on a linear combination, right? But oftentimes linear is not the best way to do it. So we could go to some nonlinear classifiers. And one example of nonlinear classification is called the logistic regression. Okay, so it's funny that this thing is a classification problem, but we end up using a regression classifier. So I can give you this example of classifying emails or tumors to spam or a ham, and that makes it more clear. So let's assume you had I mean, you're trying to classify a tumor size into a kind of malignant or let's say this is tumor size in mm, and you have and this is your x, this is your y, and you have many different data points. So you had this data. These are your data points. So meaning if the tumor was small, then it is a benign, right? So let's call this benign. This is 0, this is 1. So if it's benign, I will just give a label 0. Otherwise, I give it a label of 1. Now, as the tumor gets large, I start having a malignant tumors. So these are my data points, right? So often smaller ones are benign and the malignant ones are large. So if I try to do logistic regression on it to classify it, that's going to give me a line like this. Right, so this is a linear fit. Now, that's not the best fit, because if I have this model, then I will get values which are not 0 or 1. So it's hard to figure out what, if I want to figure out what a new data sample will have, it's not the best model to use. So the other way is to do a logistic regression. So I use a logistic function to fit the data. And the logistic function looks like this. Okay, so this is a logistic fit. Now, when I say logistic fit, basically I have to use a logistic function, which is f of x equals 1 over 1 plus e raised to power minus lambda xi. Right? So let's say this is the ith sample. So logistic function is of this form, and lambda is the coefficient, which kind of controls the slope. So another one could be like this, right? Another one could be like this. But the beauty of this logistic function is that it's always between 0 and 1. So if the x is very large, then logistic function goes to 1. Right? Because you see, if x is large, e raised to power minus lambda xi is going to be 0, and you will get 1. And if the x is very small, let's say x is 0, yeah, I mean, if so if you make x kind of go to negative, then it becomes 0. Right? So it's function really is like this. So if this is xi, this is f of xi. Function is going to be like this. If x is 0, it is in the middle, which is half. X is very small, it is 0. But again, depending on the lambda, it can be like this. And you could actually shift this. So you can actually shift this curve to anywhere. Right? It's just you have to create a displacement, and that does the trick. Okay, so let me get rid of this. Okay, so my point here is that if you have this type of data, linear fit is not well suited for this data. Okay, so now when you did regression, you actually fitted the data, but you're also classifying it. So in other words, you you've actually split up the data into binary classes, right? So it's either 0 or 1, and so this example is a this example solves a regression and a classification problem. Okay, but more general way of doing this is to use a naive Bayes classifier, or more specific. Okay, so naive Bayes is one classification algorithm that can help you create a partition to classify points. If you want to look up the details, you can actually go through it. It's not a very complicated one, but a very simple model that tells you that there is an X. The data is X, which is a random sample, and it goes to Y, and Y is 0 or 1. Right, so X is the input, and Y is either 0 or 1. Right, so the decision rule is if X is bigger than alpha, then Y is equal to 0, or sorry, Y equals to 1, and otherwise Y is 0. So you have to figure out what the alpha is. That's your classifier or partition. Now, the other way to do classification, because this is a very simple one-dimensional problem, so you could use either regression-based approach, or you could use a naive Bayes classifier to solve this problem. But generally, when you have many inputs, let's say you had a multi-dimensional input and you want to classify it into, let's say, 2 categories, visualization is not that simple. You cannot really see what line or what hyperplane divides the data into 2 classes. So oftentimes the classification is not linear, meaning you cannot really draw a line or a plane or a hyperplane to split the data. It may be a very complicated shape that splits up or divides the data, because there are so many dimensions. So one way that people have figured out is to use neural networks, right? Artificial neural networks. So we're going to see what is the idea behind neural networks and how we can actually use them to do classification problems or classification kind of tasks. So another way to achieve classification is through the use of artificial neural networks. Okay, so we want to try and understand what is neural networks are. Okay, so when we talk about neural networks, the most fundamental component is something called a perceptron. Okay, so maybe we can talk about the neuron later, but we can understand the history behind it. So this is a technique that is inspired from biological networks, right? So if you study the human brain, it has about 10 to the power 11 neurons, and each of them communicates to 10 to the power 4 other neurons. So the key idea behind this is when a neuron gets activated, it fires and sends a signal to the next neuron, and those neurons also, depending on what combination of inputs is there, it may also fire and get activated, and so on. So eventually, depending on what the input is, it goes through a very complex network of neurons and activates your different functions of the human body. So, I mean, this is the inspiration, but when we develop a neural model in computer science or in information science, we have to have a model, and one of the simplest model of a neuron is called a perceptron. Okay, so it's really a reflection of the neural activity in the brain. It's the simplest neural network. Containing just one neuron. Okay, and what it does is it takes the inputs, right, and combines them linearly to generate an output. Okay, so I mean, I can give you the figure here. So this is an example of a perceptron model, and this is something that can also be used to do the same classification problem that we saw here about categorizing inputs into two categories. So if you want to do it with the help of a neural network, you can use a perceptron, which is just one neuron. And what that does is you use a set of inputs, right? So in here, you can see your inputs are the data x0, x1, x2, and so on, right? So if you had all the inputs or all the x values, and what the outputs are, you can feed them to a perceptron. So what the perceptron is going to do, it's going to combine them linearly. So it's going to do this operation, sum wi xi plus b right? And then there is a function to it, which is f. So it combines this, and this combination result is fed to an activation function. And the output is something called the axon. Okay, so I'll label this as the linear combination of the inputs. And the f is the activation function. Now, if you want to do a binary classification, you could select f as a logistic function, meaning f will be of this form. Right, 0 or 1. And the goal is, using this data, you want to learn the best parameters of the activation function. So do you want your function to be like this or be like this? Right, so given the data, you will learn what the f is and what the parameters are, the weights are. What is the wi that best helps you classify the data. So once you have learned this, that's you've learned a model, you've learned a perceptron model, machine learning model, and next time you have a set of inputs, you can just feed this network and it will give you a result in a 0 or 1, and that you can use as a classification kind of task. So, I mean, this is a mathematical abstraction of a this is a mathematical abstraction of a neural perceptron. Right? So in here, we just have a single neuron, and it's really the simplest artificial neural network that you can have. Now, once you combine your inputs linearly, you could have many different kind of activation functions. So the example I gave you was the sigmoid function, right? So it's also called the logistic function or sigmoid function. So other models are the following. So many people use different activation function for different applications. So if you're a machine learning engineer at a company, it is your job to figure out which machine learning model you want to use. So first of all, the idea is you have to figure out what is the type of machine learning problem you are solving. Right, so question one that you will ask yourself is, do you have labels attached to the data? Okay, so if you already know what the inputs are, what the outputs are, for example, if you're solving an engine diagnostic problem, you know that if certain sensors are out, you have this fault. So you already have a label, right? So you know if these are the symptoms, that's the root of the issue. So if, let's say, you had a large data set of labeled data, input output data, then the next question is what type of learning you will employ. Again, if it's a classification problem, which is most commonly used in many applications, you have to figure out what type of classification algorithm or approach you should be using. If it's just one input data, then maybe it's very simple. You could use either a logistic regression fit, or you could use a a simple naive Bayes classifier, but let's say the data was not single input. You had many different features, many different X values to generate the Y, then you need a neural network, right? I'm not saying you couldn't do without a neural network, but in often complex scenarios, let's say like image classification, people have found that neural networks can actually perform really great. So when it comes to neural networks, you have to, again, figure out what type of neural network, because it's not a simple problem. So the simplest thing you could do is use a perceptron, right? So the problem with the perceptron is it's the simplest neuron, so you could only have a single activation combination. So if a lot of things combine together and they fire something, you can only have that one particular firing. But let's say if you want to classify an image, this perceptron may not be enough, because images have objects in them. And to be able to detect multiple objects in an image, this simple neural model is not enough. So you need to have a deep neural network, right? So that's where deep learning comes in. But anyway, so let's continue. So let's say you figured out what is the neural network model that you're using. The next thing is what type of activation function you will use. So different type of activations can be used. One is the sigmoid function, which is given here. And the property of this is that this lies between 0 and 1, right? So it can help you do binary classification. Now, this sigmoid function also can be called as a logistic function. So if you hear the word logistic function, it's nothing but a sigmoid function. Right? At its core, it is just the same, but you can have different variations. Like you can have, instead of z here, you could have minus ax plus b, right? So you could have more parameters, but at the core, it is just 1 over 1 plus exponential something. And when you have this structure, you will eventually get a function which is between 0 and 1 and has this S shape. Not exactly S, but kind of this shape, which is also seen in commutative density functions. Okay, the other function is a tan hyperbolic function. The form of that function is shown here. It's e to the z minus e to the minus z divided by e to the z plus e to the minus z. So it looks like this. And the important thing to note is that this is really between -1 and 1. And it has a sharper transition, steeper, right? So depending on what type of application you have and what type of data that you want to separate, this tan hyperbolic function can also be very useful as an activation function. And this -1 and 1 may have different interpretation in a different context. And the last one is a ReLU function. So ReLU is short for rectified linear unit. And the form of that function is simply the maximum of 0 and z. So if you want to do a ReLU z, it's just really, you will make it 0 if z is negative, and you will let it be z if it is positive. So if you look at the behavior of this ReLU function here, you could clearly see that there's a firing operation. So it's going to be dormant until something happens, right? So it simply fires as you use this function. So now this is a very important property that people want to have in a neural network, which is this firing property. And that's why people try to use it in different multiple layer networks. Okay, so it fires when the input is positive. Okay, now neural networks can also be can also have multi-layers. So this is we can refer this to as a multi-layer perceptron. And so we've seen what a perceptron is. It's simply one neuron which has a combination of inputs, but we could also have a multi-layer perceptron. Okay, so these are all types of artificial neural networks. Now, when we talk about multi-layer perceptrons, you have a set of input neurons. Okay, so let's say these are the input layer neurons. And then you have a hidden layer, which has, let's say, 4 neurons. And each neuron will actually take the output of the previous neuron and combine it in some way. So basically, every neuron will receive the inputs of previous neurons, and then it will do some operation on it and produce a result. That result goes on to the next neurons and so on. And the last layer is often the output layer. And from the output layer, you can again have a function to combine it, which is the activation function, right? So depending on what type of output you need, if it's a classification problem, you will use a sigmoid function to classify it in 0 and 1 and so on. Now, I mean, this example has one layer in the middle, what's called the hidden layer, and it has 4 neurons. But in general, you could have many layers in between the input and output layers, and their neurons can be a different numbers. So you could actually go deeper, right? So if you go deeper, let's say here you have a 3-layer neural network, and 2 of them are hidden layers, right? So you had layers in between the input and the output layer, and each of them has 4 different neurons. Now, what happens is at every step you have weights. So you kind of combine the outputs of the previous layer, multiply them with some weights, and feed it to the next neuron. And the goal of machine learning, or goal of learning in this network is to figure out what is the weights are, what is the best W's that you can use to combine the outputs of neurons. Okay. So, I mean, we're all familiar with the word deep learning, and it's essentially this idea, right? So it's having more than one layer in the neural network, and layer is kind of how many times you combine the neurons in the previous layers. So this is again a simple structure, but you could have any number of input layers, any number of input neurons, any number of hidden layers, and then any number of neurons in those layers. And that creates a lot of diversity in deep neural networks literature. So if you want to classify, for example, if you want to do an image classification, I mean, for example, here, if you take this as an example, let's say you had a lot of images of dogs, right? And you want to train a classifier, or you want to learn a artificial neural network model to classify that dog, or to classify new images as dogs or not. You can use a simple classifier, or let's say a perceptron. So what you're going to do is there's a black box in which you feed in all the images you have and the labels. So when you input a new image, your network can tell you whether that image corresponds to a dog or not. Okay, the same problem you can solve with the supervised deep learning, and essentially the inputs and outputs are the same, but inside you have these multiple classifiers. So instead of having just one black box, which was here, you will have a composition, right? A composition of classifiers. So what that means is you will have multiple layers of neurons, and then hopefully if each set of neurons, which can be represented as a black box, is well tuned, meaning its weights are selected properly, then if you feed in a new image, it's going to identify it as a dog in a very magical way, because you've actually identified features in this image and helped identify those that are really characteristics of dogs, and that can sometimes perform much superior than a single classifier, because single classifier is like a flat snapshot classification. But the deeper the network is, the more in depth it can go into identifying components, let's say eyes or nose or features of images. Okay, so let's say how we actually do the learning when it comes to neural networks. In other words, how do we train neural networks? Okay, so let's quickly oops. Okay, now there are two main algorithms that you should be familiar with when it comes to learning in neural networks. These are really fundamental ideas. Actually very useful when it comes to any type of neural network. But eventually, computers are going to do the trick for you. But it's important to understand the idea, what is happening, and what are these fundamental underlying techniques that help the computers to learn a deep learning model. Okay, so one of the algorithms is called a forward pass, and the other is called the backward pass. Okay. So forward passing really tries to do inference. So you'll see where our previously learned concepts can actually come into play. And then there's a backward pass. And this actually performs the learning. And when I say learning, it's really to figure out the weights that we have used in the model, or if it's a simple model, then it's the parameters of that model that we need to understand. Okay, so let's first look at the forward pass. Okay, so forward pass means what does the network compute? If you have a certain input, what is it that the network computes? Meaning, if you give some input numbers and some weights, then what is the output value? So I'm going to write this as what does the network compute. So going from the input to the output. And we also refer this to as a feed forward network. Okay, so for example, you had let's say we had a simple artificial neural network with an input layer of 3 neurons, and there's a hidden layer of 4 neurons, and at the output we have 2 neurons. Okay, so if you want to write the output of the network, we can say it is Hj of x, right? So this is the first layer. So let's say H is for hidden layer. Maybe I can write this down here. and J is either 1 or 2, or no, actually can be 1, 2, 3, or 4. So H is the function at the hidden layer, right? So H actually corresponds to these things, right? And then there's a output function, which is O. And it actually corresponds to what do we get here? Okay, so if you look at the hidden layer function, the active of the hidden layer. And before the activation function, what you do is you have some constant bias, and you had a weighted summation of the inputs, which are xi. Right? So let's call all of this as a linear combination of inputs. Okay, now you combine the inputs, you pass it through an activation function, and that gives you an output of the hidden layer, which is hj of x. So it will be h1 of x, h2 of x, h3 of x, and h4 of x. X being the inputs, right? So basically here you have x1, x2, and x3, right? And all of these x's are represented as this bold letter X. Now, if you go to the output layer, you are actually combining the H's, right? So you actually combine the H here with some new weights. So previously the weights are V, J, I, now the weights are W's. Okay, so you combine the outputs of the hidden layer. So we would call it the linear combination of the outputs of hidden layer. And then you again pass it through an activation function, which is in this case the G function. Okay, so it's so typically, you know, in an application of a classification example, people, what they will generally do is use a ReLU activation function for the hidden layer, and then the output layer, they can use a sigmoid function or logistic function. And that really mimics a neural activity, because in the middle, there are neurons that only fire when a certain condition is true. And then the output you have to classify, so you use a sigmoid or logistic function. So using this network of neurons, your hope is that you're able to have a classification performance which is as close as possible to 100%. So with all the data that you've been given, you want to be able to train a model which can perform great on the data set that you've trained it on, and hopefully that helps you classify newer data examples. Okay, so that's the idea. I mean, there's a lot of deep learning models that people have already trained on data. So for example, I think Google can provide you a trained model on images, right? So if you want to classify something in an image, or you want to figure out what are the objects in an image, Google has actually trained models with millions and so many images already that they have come up with a model, and if you feed it a new image, you can directly identify what are the objects inside that inside that image. So you see the whole point is to find out what are the V and the W's. So these are the parameters. That's the whole point of learning. There's no other aspect that you need to figure out. It's really what the right model is, what the components or parameters of that model are that can help you do the classification technique. And oftentimes this is a very tedious and requires a lot of computations. So you either need to have a powerful computer, or there are cloud servers and services that can help already trained models, or they can help you train with a more computational power. Okay, so we'll see one example of the training also to understand why is it a difficult process, and then if you were to do it to train a model, how would you do it? So we'll give you one example, even though it's hard to do on paper, but it just gives you an idea. And hopefully, if you are going to train your own models, then you can use the help of some computer packages that can help you do the forward pass and the backward pass to learn the model. Okay, so the last thing, basically, before we go to the next algorithm, which is a backward pass, the forward pass actually can be summarized as follows. So let's say you had a input data X. That's a sample, so it's one of the inputs, and so you go through the first step, and you can see directly that it's a ReLU function that is acting on your inputs. And then there's a linear combination sitting here. So input is first combined linearly with weights W and bias B1, actually W1 and B1. And then you perform a ReLU function on it, and then that's layer 1. After that, you pass it to a second layer, and again you do the same thing, but now you're using the outputs of the first hidden layer. So you're using H1, doing a linear combination with new weights, new bias, and then you do another ReLU on it, and you get an output H2, and finally you do a linear combination, right, with the new weights and new bias, and finally you get a a value Y. Okay, so it's done in a compositional way. So composition means that this thing here is then used in a in the input of the next operation. Okay, so if you had a sample X, then if you follow this path with all the weights and biases, then the result that you get is the result of the forward propagation or forward pass. Now the next algorithm And by the way, I just want to say here that this is a short form, right? So this really means that you have to do a summation of wi xi, I mean x, it's a w1 ij times xij, and you have a double sum I and j. Okay. I mean, maybe it's just one dimensional. So I mean, if you have a vector a vector data, then probably you just do a sum over I w1 ij times xi. So this is just a matrix notation. Now, having done that, basically the next step is to do a backward pass. So remember, we're trying to train our network first, and training means finding out the weights. And the way to find out weights is you input your data X and you figure out what the output is. And then what you do is to do a backward pass. So backward pass meaning once you learn what the output is, you try to go back and update the weights. Okay, so when you update the weights, then that's the learning. And hopefully if you keep doing it for many data points, your model will actually converge, and hopefully that's the model you have learned from the data. So backward pass relates with the learning of weights. Of weights in the neural network. So when I say this, what I mean is really that you're trying to find the matrix of weights, or W star, which is the argmin over W of the sum of I1 to n of the loss function of some data, or the outputs On and the Tn. So to figure out how good the output of the network is, generally what you have is the output of the neural network and the target result. And that loss function really tells you how far are you from the target result. So if you remember, when doing a least squares best fit, your loss function is actually a least square, is the sum of the least squares. So that's like a figure of merit of how good the classification performance is. Now, when you're in a machine learning task, again, you can have different types of loss functions that taken as inputs the result of the neural network computation, which is coming from the forward pass, and what is the target result. Okay, so generally that's the approach. So you have a loss function and you try to minimize the weights W So you find the weights that minimize the aggregate loss function. And that's the W star, um, and you try to do it in iterations. So first thing is you define a loss function. So if you were to do a squared loss function, that would be like this. So it's going to be something O minus T squared. So it's like output and minus target whole squared. Or you could have a cross entropy loss, which is defined as this. So again, these different loss functions will have different performance and depends on application, depends on who tried it and what is the result you get. Oftentimes, you know, this whole field is referred to as alchemy because there's no formula to do things. I mean, you try something and you see that this is performing great, and then you know, people try to follow you. It's really depending on who does it and how he does it. Right? So if you're using a certain loss function and hopefully with other selection of parameters, if it works great, then all is well. Okay, so let's say you had a loss function, then to minimize that loss function, you can use gradient descent. So gradient descent meaning, because oftentimes you cannot optimize something in the global sense. So what you do is you just take a update on the weights in the direction of the steepest descent. So this is the derivative, right? So it's the gradient obtained from something called backpropagation. But again, backpropagation is a very famous term used in machine learning and deep learning, and really means that you have to find the gradient. Once you have the gradient, you can actually update your weights. Right, so this and eta is just a constant, so that's a learning rate. So now when you want to do this backpropagation, so it's really a way to find out the gradient in a successive way, or kind of a chain rule based gradient determination. Right, so maybe I can write down the definition of backpropagation, just to make it more accessible to everyone. So backprop or backpropagation is an efficient method for computing gradients. Needed to perform gradient descent based optimization of the weights in a multi-layer neural network. Okay, so let's see how that works. Okay, so what you do is that you look at your data samples. So for every sample, or let's say an example input, you have the set of input data xn. N is the number of features of the data. So first thing is you do the forward pass. Okay, so that means you take that X and you pass it through the hidden layers and then you get an output O. Now, using that output, you propagate the gradients backwards using the backward pass. And then once you have the gradients, then you update the weights. Update is the following. So you just have to update the previous weights with a constant multiplied by the gradient. Okay, so let's see, how do we find out the gradient? So assuming that the error function is a mean squared error, let's say, right? So which means you had an error function which is a squared loss, right? So let's say it is sum. I'm just going to write E is the sum half OK n minus tk whole squared. Okay. Now, if you take the derivative, the 2 cancels the half, and then you're left with the just the difference between the output and the target. And let's say you call them as delta k. Okay. And now let's say your activation function is actually a logistic activation function. So which means your G is something like this. So if you take the derivative of the output with respect to the Z, you will get a function which is like this. So it's O times 1 minus O. Okay, so if you want to find the gradient with respect to the weight, you can actually use a chain rule. So you see, this is the chain rule here. So it's curly E by curly O, which you already have here. And then it's curly O by curly Z, which you can also compute because you know the activation function. And the last thing left is the curly Z by curly W. Okay, so I mean, if you look at the diagram here, there is a input layer which connects to the hidden layer with the weights, W's, and from where you get deltas, and deltas are then fed into the activation function to get the output. So I mean, the curly Z by curly W is simply the X, the data X. So overall, your gradient will be of this form. So it's O minus T times O times 1 minus O times Xi. So it's a chain method of finding the gradient. And once you found the gradient, then you can update your weights using this gradient descent rule. Okay, so it's like at one step, you just update your weights slightly. Okay, so hopefully if you do this for all the examples xi, I mean, this is only with the ith example. So if you do it for all the examples 1 to, let's say, capital N, then the hope is that your weights W have converged to some value, and then you can use that as a classifier for the future. So whenever you have new data, you just forward pass that data, and then you will get an output which should ideally be very close to your target. Okay, so we'll see one example here, right? So it's a computational example, but hopefully it may clarify things a little bit more, at least from a theoretical perspective. We can see an example of training. I mean, my goal for this lecture is that at least you know what does it mean to train a neural network, right? You've already heard these terms many times, and my goal is really to demystify the idea and hopefully enable you to use it somewhere in the future. Right? Even nowadays in the industry, people want to have machine learning engineers, and hopefully with this background, at least you understand the terminologies, and with some practice and hands-on experience, you can do great in this area. So let's say we have a simple example here with the 2 inputs and one hidden layer, and then the output. So 2 outputs, O1 and O2. So if this were the network, then you can assign weights to all the edges. So let's say the input 1 takes W1 times W3, and W1 and W2, what I'm saying. So it's H1 uses these 2 inputs, right? And their weights are W1, W2. And H2 takes W3, W4 and generates an input for the next layer, and so on. And to do the linear combination, we have to have some bias also. So in this case, we just use B1 and B2 with a multiplier of 1 as a input when it comes to generating H and the O's. So with what we have learned earlier, our goal is to train the network. So training meanings you want to find W's, right? So train the network based on inputs and given outputs. Okay, so you have some set of inputs and you have a set of targets, right? And you want to find the best set of weights. So just to have some numbers to work with, we just initialize some weights. I mean, that's a standard practice. So because you want to do feed forward, right? You want to do a forward pass. So first you have to initialize some weights, and these can be random numbers. And so that's the first step of the training. Let's say here we just use some random numbers as weights, right? And the training inputs can be actual data, but the weights are just random for the first time. Okay, now here, what I will do is to do the computations for you, but in a very brief way. So here, this thing I will be referring to as net H1. Okay, and this quantity here, I'm going to say out H1. Right, similarly, this thing I will call net H2, and I will call this out H2, just to do the computations. And similarly, this is net O1, this is out O1. This is net O2, out O2. Okay, so I have some training data. So we have training data, and the thing is that initial weights are randomly selected. And we'll assume that activation functions are sigmoid. So that means your fx is just 1 over 1 plus e to the power minus x. Right, that's an assumption that we are going to start with. And so first step, we will do a forward pass. So what that means is that we just use the input sample, and I mean, by the way, the sample has already been written. The input is 0.05, second input is 0.1. Okay, so let's see what do we, and the target is 0.01 and 0.99. Okay, so let's do the forward pass first. So what I'm going to do is first tell you what is net H1. So it's W1 I1 plus W2 I2 plus B1. Right, so and the out H1 is basically 1 over 1 plus e raised to power minus net H1. Okay, so let's say this is what it's 0.15 times 0.05 plus 0.2 times 0.1 plus 0.35 times the 1, right? So this is actually 0.375, right? And this one is basically 1 over 1 plus e raised to power minus 0.375, and it turns out to be what? 0.5932. So if you have this, then similarly you can compute, out H2, right? So similarly we can is 0.7729. Right, so our out H1, and let's highlight it. So out H1 is this. Out H2 is this. Just 0.59 and 0.77. But see, our target is 0.01 and 0.99. This is already given to us in the problem. Okay, so actually it's sorry, we are at out H2 and out H1. So again, we have to do the next step. So we have to do net. We have to do net O1 and the net O2. So I'll just do net O1 here. It's W5 out H1 plus W6 out H2. Right, so it's this one here. So in this case, it is and plus B2 is there. So it turns out to be some number, but let's just write down out O1. So it's 1 over 1 plus e to the power minus net O1. And its value is 0.751. Right, so it's out O1. Now, I'm just saying similarly, the net O2 and out O2 can be computed. Okay, so the thing to see here is this is your out O1, which is 0.751, and your target is 0.01. There's a big difference, so we'll see how this can be updated next time. Now, forward pass is complete. I mean, we have used the weights, we've used the data sample to compute the outputs. So that's the forward pass. And the next step is to compute or go to the backward pass. So when it comes to backward pass, then we have to start with the error function and compute the gradient, and then use them to update our weights. Right, so first thing is to see what the error is. And we were assuming there's a squared loss error. So it looks as it is summation 1 to n half of, you remember it's target minus output or output minus target square. Whole squared. And so it can be written as EO1 plus EO2, like loss of first one, loss of the second one. And EO1 is, I'm just writing it here, it's half T1 minus O1 whole squared. And EO2 is half of T2 minus O2 whole squared. So if I just compute it, I have the T1 here. Target was 0.01 and the actual one is 0.751. If I square it, what I'll get is 0.242748. And for the O2, it is 0.02356. Right, you can do the computation and you will figure out these are the values. Now our E total, or E total is EO1 plus EO2, and it turns out to be 0.2 0.984. Now the next step is the most important. So you have to find the gradient. So you have to find the curly E total with respect to curly W5. Right? I mean, you have to do it for everyone, but I'm just telling you what is the, let's say the first one. So it's the first update. So sensitivity of the output error with respect to the first weight is W5, can be actually written as E total divided by curly out O1 times curly out O1 divided by curly net O1 times curly net O1 divided by curly W5. It's really the chain rule of derivatives, right? So, I mean, if you look at the E total, it's the sum of the first error, which is TO1 minus out O1 squared, plus the second error, which is TO2 minus out O2 squared. So the derivative of this with respect to out O1, because that's what we require here, is simply 2 times half TO1 minus out O1 and times minus 1. So it's just going to be minus TO1 minus out O1. Compute it, it's going to be 0.7413. Okay, now let's look at the out O1, and it's by definition the logistic function 1 plus e to the power minus net O1. So the next derivative is curly out O1 by curly net O1. Turns out to be out O1 times 1 minus out O1. And if you compute it, it's 1.1868. Now the last one is the net O1. So net O1 is by definition W5 times out H1 plus W6 times out H2 plus B2. So if you do the curly net O1 by curly W5, so it's just out H1. That's our derivative, and it's just 0.5932. So therefore, our gradient will be E total divided by curly W5. It's going to be the multiplication of all three. So curly out O1 by curly net O1. So times curly net O1 by curly W5. So it's really, you multiply all three. So it's 0.7413 times 0.1868 times 0.593. And what you get is 0.082. So therefore the gradient is there, and now you want to do is update the weights. So updated weight W5 is W5 new is W5 old minus some eta times the gradient. So W5 old is 0.4 in the random weights, and eta you can choose as 0.5 here. I mean, you can choose any small. So randomly selected small step size, and then this is 0.082, which is the gradient. So if you do this, then your new W5 is 0.35, right? I mean, this is the result of your back propagation. Okay, so I mean, right now what I've shown you is just one iteration of a forward pass and a backward pass algorithm. And if you do it for all the samples, then eventually what your resulting weights will be the weights of the model that you have learned. So this process of backpropagation and the gradient descent can be repeated for all the weights to obtain the updated weights. And if the updates are repeated many, many times, then they will converge. Resulting in resulting in a trained model, right? In a trained neural network, which can be used for generating an output for any new input. Okay, so the example that I gave you is just for one data point. So you see how many computations we have to go through to actually be able to update only one weight based on one data point. So if you were to do this for all the weights, all the data points, you have to use a powerful computer at least, so that the model can be trained in a reasonable amount of time. So this example was for one data point only. We have M input pairs, or let's say an input output pairs, the gradient update will be as follows, right? So if you had many data inputs, then your W5 new will be W5 old minus eta times the sum over all the m data points. So it's curly E total divided by curly W5 evaluated at xi, yi, right? So it's called a gradient evaluated for each data point, and you have to sum over all of them. So just on a side note, I think it's important to highlight here that if sometimes the number of data points are very large, so then there's something we can do to avoid summing over so many gradients which are very, very small. So we can actually use randomization here. So if the number of data points are very large, so computing gradients may take very long. Okay, so a more efficient way is to randomly sample some, or let's say randomly select some data points and compute those gradients. So those gradients only. Right, so if instead of summing over 1 million gradients, you can just pick 1,000 and then sum over them. So these are random selected gradients, data points, and then you sum over them. And this method is it's called a stochastic gradient descent. So I'm just going to highlight this. So if you've heard this somewhere, so this is what it is. So SGD, stochastic gradient descent. And the reason it's called stochastic is because you randomly select a few points and then only do gradient descent in that direction. Now, another anecdote here, if the curly E total with respect to a weight is very small, then the weights do not get updated. Right, or update very slowly, get updated very slowly, right? So this problem, again, this is something very well known, and it's important for you to also at least know what it is. So it's called the problem of vanishing gradients. right? So I hope you're getting the point. If the gradients are very small, then your new weight will almost be the same as your old weight. So no matter how many data points you are using or how many times you're repeating the process, it's just getting stuck somewhere and it's not updating. So if you have that type of problem in the learning process, again, there are people who have suggested some modifications to kind of help you get out of that loop. Okay, now we saw the basic idea of artificial neural networks. And again, there are many types. There's one specific network that has really stood out and has performed really well. And that's the story of the convolutional neural networks. So you see, a convolutional neural network is also a neural network, but there's a element of convolution being performed. Let me pull up a simple example here and a more detailed description to help you understand what is going on. So if you look at this network, right, this is it's a fully connected neural network. So what does fully connected means is that every input is being fed to the so the result of the previous neurons are fed to all the neurons in the next layer. So that's a fully connected, right? But you could have a network where you just have partial information. So, I mean, if you do it in a systematic way, then that network can be very different in its performance. So if you look at this network, it's interesting because it's a convolutional neural network. And the reason why we say it's a just one example, convolutional neural network. And the reason why I say it's a convolutional network is because inputs are combined pairwise. So if you remember, the operation of convolution is a very interesting operation in signal processing and in information processing. I think the idea of convolution is a very important one. So in here, it's like if you combine inputs pairwise to generate the next one, it's a very simple, or the most basic form of convolution, because you have a let's say a two-tap filter where you just combine every two and then you shift by one and then combine them and then shift one and combine. So it's so this layer here is as if, you know, as if the input is being convolved two at a time. Right, and then the same thing in the next layer. So if you keep doing this in every layer, you form a very basic convolutional neural network. And the reason why I say it's a success story because of the really powerful functionality it has enabled, and that's the idea of detecting objects and images, for example. Right, so it actually learns the features and helps the neural network to fire whenever a certain feature has been detected in an image, let's say. So for example, if you have an image, what you're doing is you're performing a 2D convolution, and that generates a next an input to the next layer, right? And the next layer, again, you do convolutions, and then that generates one part of the next layer, and so on. So you keep doing convolutions to actually progress in your neural network. And every time you have a convolution operation plus some activation. And activation is generally the ReLU function here. And then there's a pooling operation, which is actually kind of just combining the outputs. So you do a convolution and then a pooling in a, how to say, sequential manner. And then at the end, you do the classification by flattening the layers and then doing a fully connected layer, and finally the softmax or the softmax activation function. Right, so let's say if there was a car or a truck or a van in an image, the convolutional operator can actually detect those objects and can fire whenever you obtain similarities in those regions. I mean, I can give you a simple example. Let's say, for example, if you had an image where you had a cat here, and then you have another sample where the cat is here. Now, just doing a artificial neural network would not detect that there is a cat in both of these because they are at different places. But if you were to do a convolutional operator, then no matter where the cat is, at some point, the neuron will fire to tell you that there is similarity between these two images, which means at least there is something common between them. It could be anywhere, but there is. And hopefully, if you learn the weights well, then you can train it on what are the components within that image. So just a basic understanding of what the convolution means. It's really you have to have a kernel and a image or whatever data matrix. So every time you have to shift the kernel and then multiply the inputs, and you will get a new output. So in this case, if you had a data matrix and a kernel matrix, then you multiply the numbers element wise, and then you add them to get a number here. And the next step, you will maybe shift the kernel here and then generate a new number, which will come here, and so on. So if there were two images which had some displacement, you would still figure out that they are in some way the same image. Now, we've seen really powerful applications in image processing, and even nowadays in videos and so many complex type of data formats that the computers are able to figure out what are the contents, what are the objects inside an image or a video or an audio. I mean, this is all possible because of the power of convolutional neural networks. Again, there are so many different varieties of them, and in so many, they come in many different flavors. So I've just put up a chart here to give you a overview of what is being used in the literature right now. So it's a compact chart of it's almost complete but not really complete. So it gives you an idea of what is happening. So if you talk about the simplest one, it's a perceptron where you just have input cells and you just have a output cell, right? So this is a perceptron. Then the next possibility is having a feed forward network, right? Where you have at least one hidden layer. Then there's something called a radial basis network. I don't know, it looks very similar to the previous one, but may have some differences, but at least the structure is similar. And then there is something called a deep feed forward network, which is DFF, and it's simply having more layers inside. And these can have different number of neurons in them, but the basic structure is like this. Now, people have already invented many different forms of these neural networks. So one of them is called a recurrent neural network, where you, I mean, there's some recurrence here. So you have a recurrent cell, right? So instead of just being a feed forward, you can actually recur, meaning you depend on yourself as well. And it has had very powerful applications in something called a LSTM, or a long short-term memory network, which people use to train time series data. Similarly, there are other examples here. It's important to note that some of them, for example, it's the deep convolutional networks. If you look at them, they are like this. So you have an input layer, and then you have these kernels, and then from these kernels you have some pooling layers, and combine them together, and then you will have some hidden layers, and then the output. So this one is called a deep convolutional network. Okay, so you can have other examples like a deconvolutional network, right? So that's kind of an inverse to convolution operator. I mean, similarly, so many different examples that people have used. So when you're implementing them, really your target is to figure out how many layers you need to have, how many neurons in each layer you need to have. And this is really something that comes through practice and implementation. So anyway, I mean, the idea here is to give you this bigger picture. So if somebody says, "Oh, I'm working on a deep belief network," so you will understand that it's nothing but a form of an artificial neural network which has a certain structure. And obviously, if you study this, there are some benefits of doing it. So every type of network will have some beauty to it, some value, and that's the thing that people can exploit. So if you become a machine learning engineer, you can study these in detail, and hopefully, whenever you're posed with a problem, you can propose a strategy and then work towards implementing it. All right, so we are now at the end of our lecture. I also had this recommendation for you guys if you want to see some animations. I think this is something I found very useful. You can actually go to this web page and see some animation, some cool stuff, seeing all the ideas in a visual way. So yeah, that's what I had for today. And that also brings us to the end of the course. So what we are left with is our, so we're, so we're left with homework 7, right? And homework 7 is actually a very, very short homework. So focused on just estimation. Okay, so it's maximum likelihood estimation and MAP, right? So it's just a few problems. So short homework, and there's nothing related to machine learning or any of the other stuff that we have talked about. So the straightforward math-based homework. And then I think I've given feedback to several people on the projects. There's still feedback on, I mean, there's still a few left that I'll get back to them on the projects. Okay, so people who have already contacted you, you can try to incorporate that and come up with a final report. The final report's due on December 17. Okay, and once you turn in your homeworks and they're graded, I will do the scaling adjustments and then remove one homework, one quiz, and I'll send you a your aggregate scores. And the last thing that will be left, it will be the project, and once that is there, you will be given your final grade. So perhaps that's all from my side. Yeah, one thing left is the course evaluations, right? So very important. I think still several people have not filled in the evaluations. I think it's very important. The university really wants to make sure everyone provides a feedback. Yeah, so make sure you take out some time and fill in the course evaluation. And that's it. I think my goal in this course has been to give you an overview of the many different ways information is processed, is stored, is transformed to make meaningful use out of it. And we've seen, I think, a very broad variety of different aspects of information engineering, and I hope you you learned something out of it, at least something you didn't know before. And if that's the case, I think I've been it's a success for me. Yeah, and I hope you had a fun learning through this course. So anything you want to ask, you feel free to send me an email, or you can ask right now. Otherwise,
when is the homework due?
Yes, homework is due next week. So it's again same Tuesday. I don't know what's the day. Let me see. So next Tuesday is the December 14, right? Yes, homework is due on a Monday, like always, December 13. Okay, so,
And it's homework number 6, not 7.
oh, is it? Also quiz number 7, right? Okay, so homeworks are 6. Yeah, thank you. Yeah. Okay, so I guess that's all. And feel free to drop by later on when you're on campus.
What's the homework 6 gonna cover, Professor?
Yeah, I just told you it's basically estimation, right? So we
Oh.
studied maximum likelihood,
Focus on estimation.
and MAP. It's like if I tell you the data is distributed according to the normal distribution, what is the best estimate for its mean and what is the best estimate for its variance? So probably you have to review last lecture material. Okay, any other questions?
I actually have a question regarding the one of the feedback. Should I ask it now or like after the recording? You want to close the recording and then I can ask it? I don't know.
Yeah, I can close the recording here and then we can,
Okay.
I mean, is it a general?
Yes, it's a feedback. It's a general feedback question. Like,
Okay, it's for everybody, right?
no, not for everyone. This is specific to my feedback, but it was
specific,
very
okay.
short. Yeah.
Yeah, okay, then we can, so everybody else can disconnect and we can continue.